Hey everyone, my wife keeps nagging me to weed the garden, so I've decided to do her one better. I'm going to build an autonomous robot that can do the weeding and hopefully some other gardening as well. So this is the robot so far, and I've mostly been getting the robot arm to work in ROS2 control, and that's going to be the focus of this video. But before I get into the weeds of how the robot arm works, I'm just going to give you a general description of the overall robot. So for the chassis, I've used the Go Builder system, and it's four-wheel drive because I'm going to be driving on some in the garden, so on some fairly rugged terrain. And I've put the bill of materials for this build up on my GitHub, so you can look at that. But in the past, I found the Go Builder stuff to be pretty good. And I've also got, this is a depth camera that I've got on the front, and this is just a homemade depth camera. So here I've got a Arducam time of flight camera, and that's an RGB camera. So this camera gives the depth and this camera gives the color, and then I match the two up together. And I've got them connected at the back to this Raspberry Pi 4, which I just had lying around. And I needed the Raspberry Pi 4 because the time of flight camera uses this MIPI CSI port. And then this is a PCA 9685 board to drive the servos. I've got two servos for the pan tilt, so one to make the camera go up and down and one to make it go from side to side. And then I'm going to get this working with the arm, like for a hand-to-eye coordination thing, but that's going to be in the next episode or maybe the episode after, so I'm going to put that away for this episode. So the brains of the robot, I'm using this mini PC, and I was going to use a Raspberry Pi 5, but I decided to go with a mini PC. I mean, it's not that much more expensive, and you do get a fair bit more, I guess, processing power. And we've got two of these USB ports here, plus a USB-C, plus there's another two USB ports at the back, and an Ethernet port, and an HDMI output. So this is pretty good. I mean, it does, like, I can do like YOLO models in real time, and I can, at the same time, use the navigation stack because it's got to calculate paths for navigation. It does use more power than the Raspberry Pi 5, but the advantage there is it does have a sleep mode on it, so I guess you can put it to sleep if you need to, whereas the Raspberry Pi 5, I think it's more difficult to put it into sleep mode. And that's something you do have to be careful with, I guess, when you're running a robot, is because you do have to power it by battery. And I've got three batteries here. I've got three 3S LiPos. So two are in series, which are connected to the motors through a 12-volt converter. And then one is driving the other electronics. And then I've got another battery pack for this, which isn't shown here. But I'm still deciding whether I'm going to use that or something else. But you'll see that, I guess, in later episodes. And then this is an RT LiDAR, which I'm going to use for navigation. So that's just a cheapish one. And then on the top here, I've got the ESP32. I'll just bring the camera closer so you can see. There, see, I've got the ESP32, which is connected to the motor controllers. That's collecting all the data from the interrupts as well, which are the encoders on the motors. So if you're going to build a robot, it's important to make sure that the motors have encoders on them, so you can see how far they've moved. And then I've got like some power stuff as well. So this is a 5-volt converter, another converter here. You can't see that, that's running at 7.4 volts. That's to power the robot arm. But like I said, I put the bill of materials up on my GitHub, so you can have a look at that. So in the next scene, I'll show you basically, I'll take you through how I get the robot arm up and running on the simulator, and then the hardware interface for that with ROS2 control. Josh Newen's Articubot 1 provides a good foundation template for more complex robotics projects. So I'm starting with that and making it more advanced. So now the code is up on Josh's GitHub repo. So he's got three branches. He's got a main branch, a humble branch, and a new gazebo branch. And the main branch is written in ROS Foxy with Gazebo Classic. The humble is ROS2 Humble, and the new gazebo branch, The one that I'm using is written in ROS2 Jazzy with gazebo harmonic. So on the gazebo install page, it basically tells you which version of gazebo you need with which version of ROS. So I'm using ROS2 Jazzy, so I need gazebo harmonic. So you need the one with the green tick. Don't use the one with the yellow lightning bolt. It says it's possible, but you'll find something that doesn't work, and that'll be a bottleneck for your whole project. So now I've cloned this into my workspace, and I'm putting it in its own workspace, separate from my actual project called Josh WS. So I just want to get this working, make sure I can get the simulation working. I only need to get the simulation working because every robot is going to be different, and I want to make sure I can get this project working in simulation before I start building on it for my project. So we'll launch the project. And it uses a gamepad. I'm using this gamepad here to drive it around. And my gamepad is like just a cheap one with a wire, the one that I've got connected to my laptop. And I'm developing for the robot on my mini PC, which is on the robot. So for that, I've got this gamepad here, and I'm going to implement the inverse kinematics with that a little bit later on in the video. So let's get articubot 1 working on the simulation now. So for me, to get it working, it didn't actually work straight out of the box. I did have to make one small tweak, which was to add this use stamped false to my twist_mux.yaml file. So now we can source our workspace and then launch it with so Josh has written the launch file for us, which is pretty nice. All right, so here we've got gazebo, and over on the left, I've got rviz. So I'm just going to drag that open. All right, now let's try and drive it around with this. Okay, so it drives around in gazebo, but not in rviz. And to get it to drive in rviz, we need to set the fixed frame link equal to odom, and now we can drive it around. All right, so now we've got that working, we can kind of use this as a template with a launch file and configurations just to write our more advanced project. Okay, so now I'll just show you the robot arm that I'm using. I'll just put that in view. So most manufacturers of robots or robot arms will provide you with a URDF file along with the STL files, which can be used in the URDF for both visual and collision geometry in simulation environments and rviz. So I've managed to find the URDF for this robot, and so this is it here, and I've managed to find it online, and it links into these STL files, which gives it a more complex structure than just cylinders or boxes. Now that we've got the URDF, we can visualize it in rviz. So that's the first step. The first step is just to see if you can visualize it in rviz, and then if you need to adjust anything, if it matches your robot, or if there's an extra piece on there that's like an extra piece or a different effector or something. So let's cd into my development directory, and we can launch into rviz from there. All right, so we've got the robot arm here, and over here we've got the joint state publisher GUI, and we can move the joints with this GUI in rviz. So we can move the end effector, the fingers, and we can move the wrist, and then the elbow. All right, so that looks good. I mean, that looks pretty similar to the one I've got here. So everything looks all right, similar end effector and same number of joints and similar rotations. The next step is to get the robot working in gazebo. So first we get it working in rviz, then in gazebo, and then on the real robot. Now we don't go straight to the real robot, although it's quite tempting, just because there's a lot of troubleshooting and planning that we might need to do, especially if we're using something like ROS to control or move it, If we're just publishing joint angles and then sending it to the robot, then it's quite simple. But if we want to do more complex tasks, like planning and transforming between the camera and robot coordinate frame, then it's better to approach this quite carefully and do a little bit of stuff in the simulation environment. Okay, so when I try to launch this in Gazebo, it doesn't actually work. And it doesn't work because of this package keyword, all right? So when Gazebo sees this URDF, it sees this package keyword and it thinks, okay, that's in my models directory. So Gazebo has a built-in models directory, and it looks for this directory path and file in its built-in models directory. And one way to fix that is to link the built-in models directory with the package shared directory. And you can link that in your launch file. Another way to do it, which I prefer because I thought that way was a little bit messy, but it's probably more professional, is to use this $find xarm description. So this will find the absolute path to the xarm shared directory, and this file will tell Gazebo, instead of looking in the models directory, to look for the absolute path on the computer. So then Gazebo will be able to find the STLs if we do this. All right, so I've changed that. So now we can launch it in Gazebo. And I've put my launch files up on my GitHub so you can have a look at those. Okay, so now when we move the joint state publisher, GUI, it moves in rviz, but it doesn't move in Gazebo. To get it moving in Gazebo, we have to bridge the ROS topics with the Gazebo topics. Well, that's one way to do it, but I'm not going to do it like that. I'm going to use ROS2control instead. And ROS2control bypasses both Gazebo topics and ROS topics and can communicate with minimum overhead. So it's a good way to communicate with the hardware. And now I wanted to get ROS2control working in Gazebo because I want to get it working on the real robot. And one of the ways to, I guess, troubleshoot it along the way is to get it working in Gazebo. So ROS2control has two main parts. These are the controller manager and the hardware interface. So this is the controller manager configuration here that I've got open. And the controller manager controls everything on the software side. Things like deciding how the motor is going to move and the velocities, accelerations, and positions of the motors. And then the hardware interface issues instructions directly to the hardware and the motors. And it takes readings from the hardware. So, I mean, the name is quite self-explanatory. So this config file has two controllers. It has a joint trajectory controller and a joint state broadcaster. And the joint trajectory controller decides the positions, well, the angles of the servos on the arm, and the joint state broadcaster broadcasts the feedback. Now down here, I've got the configuration for the joint trajectory controller. So it's basically like a node that publishes on the command interfaces and subscribes to the state interfaces. So for example, if this was a ROS node, the publisher namespace would be these joint names. So these would be our publisher namespaces. And the publisher topic would be command interfaces / position. And the subscriber namespaces would be our joint names. And the subscriber topics would be state interfaces / position and state interfaces / velocity. So the state interfaces are published by the hardware interface, which is kind of the opposite. And the hardware interface subscribes to the command interfaces. So this is the hardware interface configuration file here. But I'll talk a little bit more about this when I go through the C++ code for this. So that's basically how the controllers work. So I'll show you that on Gazebo. So in my launch file, we have to spawn these controllers. So we spawn this controller here, and then the joint state broadcaster, we spawn it here. But when the launch file, we've got this spawn here, and like, how does it know what this is when we pass this in as an argument? And the answer is, it comes from this xarm. It's defined here in the xarm controller's YAML file, which is buried kind of deep in the robot description. So if we worked our way backwards from, this is like the launch file is like the top level file. So if we work our way backwards from there, so if we go up to the top of the file, we launch this, we run this arm.launch.py, and this launches the xarm for the xarm, and that xarm, you go down a couple of layers and you'll find this file, the xarm controllers YAML file referenced. Okay, so now we can launch the sim file and we can get our robot to move in Gazebo. So now we've got it launched in Gazebo, we need some way to pass commands into the hardware interface plugin from the controller, and we can use RQT for this. And I couldn't get RQT with the controller manager to work in ROS 2 Humble, but when I started in Jazzy, it worked fine. So let's launch up the RQT sliders. Okay, so our sliders are over here, and then we've got our controller manager definition here and our High Wonder xarm controller here, and we press this button to get it started. Okay, we have to speed it up a bit, otherwise it's really slow. All right, so this should be the gripper. This is the wrist. Rotation. This goes. So everything's working now in Gazebo with ROS 2 control. So now let's get it started on the real robot. I've remote desktop now into this mini PC, which is connected to the robot arm. So I can launch the hardware interface now on the robot arm, and hopefully we can get it working with the slider. So I just send out a few commands to the robot arm when I launch it, just to make sure everything's working. So it comes up now in rviz, and let's just organize this. Let's just get it facing the same direction actually as the real robot. And let's just rearrange things a little bit. So now we can control this with RQT, and we can actually run RQT either from the remote desktop or from the laptop, and we can actually run it from any computer that's on the network, provided we expose the container to the network. So let's run it from the laptop. All right, let me just bring it over so we can see it a bit better. Let's see if everything lines up. So this is joint 6, which is the bottom joint. So let's see if it rotates in the same direction. Okay, so both the rviz and the real robot arm rotate in the same direction when I turn this, so that's good. Now this one. So the real robot arm moves forward, but the rviz robot arm moves backwards. So joint 5 is out of line. Joint 4, let's have a look. So both move backwards when we move it below 0, and both move forwards when we move it above 0. Okay, joint 3, above 0. The real robot arm moves backwards, but the rviz robot arm, let me just move that a little bit over. But the rviz robot arm moves forward. So joint 5 and joint 3 are moving in opposite directions between rviz and the real robot arm. Now joint 2. Okay, now joint 2 is moving in the correct direction. All right, so the only ones we need to change are joint 3 and joint 5, and the way we change it is actually quite simple. We just have to go into the URDF and change the sign on the direction of rotation around the axis. So let's get out of here, and this is our URDF here. So we want joint 5, which is this one. Let's just move this out of the way for a minute.
joint 5, which is this one here, and this is our axis of rotation here. And now we just have to change our axis of rotation to the opposite direction for joint 5, and then for joint 3, for this one, again, we just change this here to the opposite. So just put a minus sign there, and then this should fix everything up. Now let's relaunch everything. Okay, so now it was joint 6, so let's see if that's working now. Oh no, sorry, it was joint 5, wasn't it? Alright, so they're both moving forwards. And joint 3, let's see if that's moving in the right direction. Oh yeah, they're both moving backwards now. Speed this up a bit. And now they're both moving forward. So everything's moving in the right direction. This is very important actually, because if we're planning paths with MoveIt, or if we're transforming between frames from the chassis frame or the camera frame to the robot arm frame, then we need to make sure that all our directions, what we think is as the positive angle, is actually going to be the correct direction. All right, so now we've got all that sorted out, we can move on to implementing the inverse kinematics with this controller here. Hey everyone, I'm just going to give you a really quick demo and explanation of the simple inverse kinematics on this robot arm that can be controlled with this gamepad here, so I can use that for manual override when the robot's operating in autonomous mode. Alright, so now the first thing I have to do is launch the robot, and I've just copied this launch file from Josh Newen's articubot 1, and I've made a few adjustments. So I've adjusted the robot chassis, so I'm using my robot chassis in the exact rows, and I'm using a 4-wheel drive diff drive controller, and I've added the robot arm. So let's launch that. So now that that's launched, I can show you the demo. So this control here is for the robot wheels, and this one are for the robot arm. So if I move this forward, I move the wheels, and then the other direction, and then I haven't actually included the controls for the robot arm in my launch file, my original launch file where I launched the whole robot, because I'm still working out how I'm going to integrate it with other methods of controlling the robot arm, so like autonomous control. So let me launch that. This is the joystick launch file, which launches the inverse kinematics controller for the gamepad. All right, so for some reason, I point the robot arm down when I launch it, and that was just like what I thought was a good initial position at the time. So this control here is to move the robot arm up and down, and this control here is to move it backward and forward and side to side, and then this one here, the side control, is to open and close the gripper. All right, so up, and then sideways, other way, then down a bit, and then forward, backward, and then back a bit, forward, all right, so I'll just give you a quick explanation of what's going on. So because this robot is constrained to move in one plane, basically it's got the rotational symmetry, so wherever it's rotated to, it's going to be constrained. This robot arm is going to be constrained in this plane. So I've only implemented a two-dimensional inverse kinematics in the X and Z plane, basically. So I'm only solving for the angle on this servo and the angle on this servo for the XZ position of this point here. And this end effector, I've constrained that to be straight when it's about halfway up, to be pointing up, when it's above a certain, when it's all the way up, and then to be pointing down when the Z is below a certain level. And the reason I want it pointing down when the Z is below a certain level, so that moves it forward. The reason I want it pointing down when the Z is below a certain level is because I want to pick things up with it. So I want to pick things up off the ground and then I want to pass them up. And the other reason why it's good to do it that way is because it gives me an extra constraint to solve for these angles, to solve a complete solution for these angles for the inverse kinematics of this position here. Of course, if I'm going to operate it in autonomous mode or do more complex tasks, I would probably have to use some more complex software. But this gives me a really good way to manually control it. And then this one here opens and closes the gripper. I guess the other thing I have to point out is there's a bit of troubleshooting you have to do with this gamepad here. So if you're in a container, and I would strongly recommend using a container, because if you upgrade your version of ROS, then you don't have to upgrade your whole operating system. Or if you install multiple versions of the same package, you can just purge your container and rebuild it. So what you have to make sure if you're using the gamepad is you have to make sure that the container user is in the input group. Okay, so this is the input group here, and the ID of the input group in the container has to be the same ID as the input group outside the container. And if you can't even get the gamepad to work outside the container, then you would have to create an input group outside the container. And I put some troubleshooting steps for the gamepad here on my GitHub. So in docs, troubleshooting and tips, gamepad troubleshooting, there's managing the input group on Ubuntu, which you need for the gamepad. In the next scene, I'll take you over the Python code that I'm using to control the robot arm with the inverse kinematics. Okay, I will see you in the next scene. So I'm just going to go through the code with you for driving the robot arm with the gamepad using inverse kinematics. So most of the work happens in this joy listener class here. So we initialize our base class. Our base class is robot GUI. So we initialize our base class with the trajectory topic. So the trajectory topic is this. This has already been launched by our launch file. So this kind of already exists. And this joint slide, that's just a name. That can be any name, but this is basically like a legacy name, because when I originally wrote it, I was originally using sliders because I couldn't get RQT to work. But then I got RQT to work, so it became legacy. So let's go have a look at this superclass anyway. So this does a couple of things. It defines a publisher. So this publisher publishes the calculated positions to this topic here, this joint trajectory topic. And this joint trajectory topic is the one that controls the robot. So we can basically, now we've exposed this joint trajectory topic, the controller exposes this, we can control the robot from any node on the network. All right, so we define a publisher to publish our calculated positions to the robot. And then I guess the other thing we do is we populate these, the joint names and joint limits. These are the two important ones. So the joint names we get here, get joint information, and we get those from this. So we don't actually hard code the joint names. We actually get them from the joint trajectory controller, which is here. So this way, if we want to change the robot arm, we want to use a different robot arm or the same robot arm with different joint names, then we only have to update the joint names here in our controllers.yaml file and in our Xacro file. We only have to change the joint names in two places. We don't have to change the joint names anywhere else in our code. Because we basically get them on the fly from the trajectory topics. So the next thing we do is we declare our parameters, use sim time. We only use sim time true if we're running simulations. And then we define our joystick states and some of our parameters. But I think what's more important is this. So this is the subscriber, which subscribes to the joystick, which subscribes to the gamepad commands. And the gamepad is, I'm using the joy package, and it runs on the joy node, and it publishes to the joy topic. So the commands from the gamepad are publishing to the joy topic, and then this node subscribe. So this is actually a node, this min joy listen. This node subscribes to the joy topic. So once it subscribes to the joy topic, it gets the inputs that it wants from the joystick, and it turns those into positions, and then it publishes those positions back to the controller. So this is where it calculates the inverse kinematics. So let's go to the definition of that file, and it's just using a simple two-dimensional inverse kinematics. And I've just copied these formulas from one of the YouTube videos on two-dimensional inverse kinematics. It's not that difficult. And then the only other angle I calculate is the angle of the end effector, which is the angle which is basically interpolated. So this is based on alpha, and this is interpolated depending upon how high it is. So if it's right at the top, then the end effector is pointing straight up, and if it's down below a certain level, if it's below, I guess, 0.05, then it's pointing straight down, and it's pointing straight down, like I said, so I can pick things up. And then the other one is this send position, and this send position just sends the calculated positions, publishes them to the trajectory topic, and that'll send it to the robot. In the next scene, I'll take you through the ROS2 control for the hardware interface for the robot arm. I'll see you in the next scene. I'm just going to go over the ROS2 control hardware interface for my robot arm. So in my ROS workspace, I've got 4 packages, and these are all up on my GitHub, but I'll just go through them with you quickly. So autonomous robot, this is the one that I've adapted from articubot 1, and it's basically, I've rewritten it for my 4-wheel drive robot. So this contains the URDFs for the chassis, and as well the configuration for the gamepad to control the wheels, and the RP LiDAR and the camera. And then the diff drive Arduino contains the hardware interface for the differential drive for the wheels on the chassis. And this was written by, well, this was based on the one written by Josh Newen, but I updated it for a 4-wheel drive robot, and I'll go through that with you in the next episode. And then the xarm description contains the URDFs for the xarm, as well as the gamepad configurations and the gamepad code. And then the xarm hardware, this is the hardware interface for the xarm, and that's what I'm going to talk about now. All right, so this is all written in C++, and before I go through that, we'll just have a look at the .hpp file. So this xarm hardware class is basically inherited from the hardware interface system interface. So most of the hardware interface classes inherit from this system interface class. So the system interface class implements these functions here: on init, on configure, on activate, on deactivate, on cleanup, export state interface, export command interfaces, read, write, which we implement in our C++ file, and I'll go through those with you soon. And then we have like some members. So we have the serial comms, which is I've used a smart pointer for that, and that communicates with the serial port. So I'm using serial communication, and the robot arm has an ESP32 on it, so I could use Wi-Fi, so I might update to Wi-Fi at some stage. I have written Wi-Fi bridges for this before, but I just thought for the robot, since everything's so close together and I might be operating it outdoors and stuff, I just thought it would be better to use serial for now. And then these are the joint position commands, which is like a vector of the position commands received from the controller manager, and then joint position states and joint velocity states, which is feedback from the robot. So let's go to the C++ file now, and we can see what everything is. So the first function is on init, and we have this info object. Now this info object is a member of the base class, all right? So it's a member of this class here, the system interface class. And what this object does, and what this info object does, is it basically gets all the parameters from the URDF that are defined between the ROS2 control tags, all right? So this is part of our URDF Xacro, and we have these ROS2 control tags, and everything that's defined between these two tags. So we're using this xarm plugin, this one that we wrote, xarm hardware xarm plugin, and this is the one that we wrote. So it knows that this is the one it has to use to get all these parameters, and we've defined all these parameters here. These ones we're not actually using, but I just left them in for good measure. So with the serial port, the baud rate, and the timeout, they're our serial communication parameters. And then we've got all our joints defined. Let's move down here actually. So we've got our xarm2 joint. So all our joints are defined in this kind of Xacro XML type file, and we've got our command interface and our state interface is defined as part of our joints. So it's got all our joint names, and the joint names in here have to match up with these joint names here. Okay, so basically this info contains all the information that's in this Xacro between these tags, between this ROS2 control tag and this lower ROS2 control tag here. All right, and then this one is the one that we use for the simulation here. But if we're running the real robot, we use this, and there's not too much difference except for the plugin. So this is the plugin for the simulation, and then this is the plugin we use for the real robot. Okay, so so now this info knows all about everything, that's all the joint names and everything that's on the robot. So what we do is from the info we can basically populate our vector of joint names that we've defined. So we've defined it here, and we can populate that with all the joint names that are supposed to be in the controller, so that are defined in the URDF and that the controller should know about. And remember, I said before, these are like our namespaces that we publish on. So the controller is publishing the commands and the hardware interface is subscribing to the commands. And then we just assign enough room, like some memory for our vector of commands and states. All right, and then we initialize our serial comms object here. Well, we initialize some memory for it. All right, so then in our configuration, we configure all our parameters. And so the info, like I said, the info has all these parameters here, which are defined in our Xacro file. So these param with these names, these are all defined here. So our info object, which is an object from our base class, our base system interface class, knows all about these. So we can just include them in our class here, and then we can use them to initialize our serial comms, because I mean the main thing that we need is the serial port, because this can vary. So we can use our launch file to feed this in as a parameter as well, because in our Xacro we've got it defined here as a parameter. All right, so then we initialize our serial communications, and then on deactivate we don't really do anything. We can do something like send an emergency stop to our robot arm or something, just to make sure it doesn't move or hurt anyone. And on cleanup, we just basically release any hardware resources. So here we stop the serial comms. So we basically give up control of the serial port just in case another process wants to take control of it. Now, this one, export state interfaces, I'll come back to, and export command interfaces I'll come back to, because first I want to get into the read function. So these ones, gripper to radians, radians to gripper, these just convert between units. So the gripper is in centimeters, but we want it in radians. Now this read function, so every so at the frequency, at the refresh rate of the controller manager, the read and write functions get called. So these functions, that's the read function, and this is the write function, and they read and write to and from the hardware. Okay, so these get called at the refresh rate of the controller. So in our my controllers, in our xarm underscore controllers.yaml, we've got our update rate at 10 hertz. So that means that these functions will get called 10 times a second, right? So when this read function gets called, it reads, so it calls the serial comms object, and it reads the positions of the robot arm into the joint position states, and it calculates the velocity as well, because this time here, this period, gives the time between subsequent calls of the read function. So the period is the time since the last time this read function was called, basically. So we read our joint positions, and we into current positions. We have to do a little bit of massaging, like call hardware to ROS, just to convert them into radians, and then we have to convert the gripper one into centimeters, and we read it into our joint velocity states. Now this joint velocity states and the current and the joint position states, these get broadcast back to the robot description, and these get fed back to the controller manager. But how does the controller manager and the robot description and the state broadcaster know where to find these? So we're just writing to this vector that we've defined in our class, but how do we know where to find it? And the answer is in this function here that I said I'd come back to, this export state interface function, right? So what we do here, when we export the state interfaces, we tell the state interface that this joint position states is where to find the feedback, basically. So the state interface, remember, that's like our publisher. So the hardware interface publishes to the state interface, and the controller manager subscribes to it. So we're basically saying, all right, we're publishing on, this is position, we're publishing on the topic position, and this is the reference where we're publishing. So whatever we write at this address, because the and gives us the address, whatever we write at the address of this number is basically going to be what's published, what's exposed. So we're exposing this to the rest of ROS and our joint names. So remember, our joint names are here, and these match what's in our Xacro file. And so these were like our namespaces, and then our position is like our topic. Okay, and then it's similar with the command interfaces. On our write function, we get these joint position commands, and these joint position commands are updated because this joint position commands has been exported by it's been exposed when we here. So when we've already exported the command interface here, so it already knows that this is, so the controller manager is already writing to this address here, to the address of joint position commands at that number, at this integer, which corresponds to this joint name. All right. So that's basically it. So basically all we have to do is write to these joint velocity states and joint position states and read from these joint position commands, and it kind of everything else is kind of handled by the base class. We've got a few auxiliary functions down here, and I'll let you read those. And then we export the plugin class here. That's just so when we define it here in our Xacro file, it knows where in the package to find this plugin basically. And anyway, so that's basically the plugin. That's basically how it's implemented, and you can have a read through this. If you've got any questions, just leave them in the comments and hopefully I'll be able to answer them. The last thing I'm going to show you is a MicroPython code that I've got running on the ESP32 that's connected to the xarm. So to flash this to the ESP32, I'm using the PyMaker extension in VS Code, and it's got pretty bad reviews, but I've actually found the PyMaker extension is pretty good. So it has a number of files. It has this bus servo file which communicates with the servos, and then the main file which runs this run serial thread, and this basically receives serial commands and then executes them and sends back commands. So the only two commands I've got going at the moment is to write to the motors and read the buffer, but there's a whole bunch of other commands you can implement in here as well. So if you want to have a look at this, it's up on my GitHub in the xarm software MicroPython xarm control directory. Okay, thank you for watching, and I'll see you in the next video.